Welcome. Once again, my name is Arya Hakimian, an application scientist here at C-Therm Technologies. Today, we are taking a look at the dynamic mechanical analysis of tire tread compounds. I'm joined by my colleague, Arya Sharostembik, who is a laboratory scientist here, who will be coming in a little later in today's session. But the main, I would say, focus for today's talk and who will be going into the bulk of the content is our guest speaker, Dr. Richard Pazur. He is a lead scientist focusing on elastomers at the Department of National Defense. With that being said, I'm just here to get a little bit of an intro going. Wanted to start off before we go into the bulk of today's content with just a little background about C-Therm. Of course, today's focus is on DMA. C-Therm Technologies, however, we are focused on the development and measurement of thermal conductivity, specifically the transient class of measurement technique. So again, while not the focus of today's talk, I did just want to introduce this to folks on the line that may be interested. Our core instrument is called Trident. You can see a picture of the instrument on screen. Trident was developed as a modular platform. It offers multiple methods for thermal characterization using four transient methods. The idea behind Trident, we like to reference this quote here from Abraham Maslow: when all you have is a hammer, everything looks like a nail. And again, the idea behind this is in terms of the measurement of thermal conductivity, oftentimes, trying to take a really good method of measurement and applying it on a sample that it just really wasn't designed for. This is where we can get into some issues with, poor data or some unwanted errors. So again, the idea with Trident is you can take more of a toolbox approach to select the best method for the task at hand. So again, just wanted to introduce that quick little bit of information about C-Therm and our Trident platform. For those that may be interested in thermal conductivity, we do have a method selection guide available as a free resource download on our website. This is a great bit of information for folks that may be new to the thermal conductivity space or folks that maybe are just looking for a little refresher on what options are out there. So again, while not the focus of today's talk, just wanted to put a little brief intro there. There is a QR code on screen that you can scan if you do want to take a look at that in further detail. All right, but from my side, that completes our little introduction to today's session. At this point, I'm going to, if I can find my mouse, there we go. Go ahead and I'll stop sharing here. And at this point, it's my pleasure to invite our guest speaker, Richard, on screen to take us through the bulk of today's session. So thank you, Richard. Take us away.
Okay, thank you, Arya. Do you see my presentation?
It's coming up there. I think if you go to presenter mode, should be good to go.
There we go. How's that?
Perfect. Looks good. Thank you.
All right. Thank you for that wonderful introduction. I saw you had some nice photos there as well, showing the one of our, I think it was of our lab 3s there up north. They're in the snow as in your first presentation. So thanks for showing that. So again, this presentation will be talking about the DMA. And again, thanks for the video as well, because that also gets everybody into the mood to talk about DMA and about what we can do with this piece of sophisticated equipment. And I'm going to show today some work that we've done. It's been a few years now, looking at predicting tire performance with the DMA. Now, this work was done in collaboration with Akin Rubber Development. I couldn't do it all alone. Actually, Akin Rubber Development, they do have the experts looking into tire and tire testing, and particularly with Ed Terrell. We did a lot of collaborations before in the past. Ed, as you may know, has now retired, but Ed formerly was at Goodyear, and he knows lots about tire compounds, about tire testing, especially with the DMA. So I learned a lot from Ed and how to use the DMA to predict the tire performance. And before I change slides, I just want to thank again C-Therm Technologies for allowing me to present today. It's a great time to present. And the talk today I'm going to be giving is work that I actually published alongside with Akin Rubber Development about 12, 13 years ago. We presented this paper at the ACS Rubber Division in Cincinnati. And like a lot of ACS papers, there are a lot of great ones, and they just stay with the ACS Rubber Division. You have to get them published elsewhere to get them read as well. So we published it in the Rubber World. And if you look at the December 2013 issue, it's the effect of deformation mode and prediction of tire performance by dynamic mechanical analysis. So I'm going to go over that work that we did because I thought it was a nice, good a summary of how we can apply the DMA to tire testing. Now, let's start off with, I'm going to have to move this out of the way at the top here. So dynamic mechanical testing analysis, what is that? So the theory behind it, and I'm not going to go into, let me see here. Here we are. I took some of the theory from the actual Metravib literature because I thought it was very good and appropriate. I didn't want to dive into a lot of details about DMA testing, about the theory, but I'll just give you a short overview. Because if you look at this first diagram, what do we do in DMA testing? We have our sample here. This is a cylinder. And what we're doing here, we're applying a strain. Now this strain, the D is displacement. It's a sinusoidal sort of oscillation that we're applying to the specimen. So it has a certain displacement, dynamic displacement, and it also has a frequency. So when you apply it to the specimen, what happens is afterwards, the specimen is going to react to that strain, applied strain, and with a stress. And the stress here is given by the blue here below. And you can see that they're not in the same shape and form. Why is that? It is because of the fact that if you look down here at the next one, we're dealing with viscoelastic materials. If we had a completely elastic material, those curves would superimpose upon each other. But because we're talking about viscoelastic materials, there is a lag between them. So if you look at this graph here below, you can see that the lag between them is called the loss angle. Now, loss angle is related to the amount of viscoelasticity that we have in the material. If the material was completely elastic, as I mentioned, those two curves would superimpose. If it was completely viscous, there'll be a 90-degree phase difference between the two. Now, what we can do is with this data is that we can get the output, the force output, and the machine, what it does, it measures a complex stiffness. And that complex stiffness with mathematics, and to make things easier, I'm just showing you this diagram here, the upper right, where I have it in the tension mode, represented by a capital E. So the E star is our complex modulus. The complex modulus can be decomposed into the storage modulus and into the loss modulus. So storage modulus is the actual, represents the elastic work of the material. That's what we want in our compounds. And the loss modulus represents the dissipated energy when we do work on the compound. The tan delta that I mentioned earlier, so related to the phase difference, is this a relationship? It's the ratio of the loss modulus divided by the storage modulus. And the tan delta is very important in tire testing because it represents the hysteresis and also the heat buildup of the compound. And that can be easily measured with a DMA. Let's talk about tire deformations during the motion of a tire. Oops, there's a message here. Here. Tire deformations. So a tire, of course, let me see. Oh, it's not. There it is. Okay. So a tire. I had a heck of a time trying to find pictures of tires and what I wanted, so I had to draw one myself. A tire, of course, is going to be under a constant stress due to the load, right? So that's the arrow here going down on a tire. And a tire that's going to be in motion is going to be churning. And when it hits the pavement or the surface here, you're going to be having bending modes taking place where it hits the surface and then it's released here at the end. And those bending modes are strain modes. There's also tangential and shear strains also taking place with the pavement. So I'm not a tire mechanics expert. So that's just in a nutshell, very briefly, what sort of deformation modes are we seeing with tires? And the nice thing with the DMA is that for us to test tire tread formulations under dynamic conditions, we can use the tension compression mode, the shear mode in particular. The torsional mode can be used as well, but as far as I know, it's used by you need other equipment to use to measure the torsional deformation. So the goal of today's talk is, and oops, doesn't seem to want it. There it goes. We want to test a model tread compound using the compression, tensile, and shear deformation modes using the DMA. Simple as that. And we want to check the theory as well. So according to the theory of rubber elasticity, given the fact that we have an incompressible piece of material, it is known that the tensile storage modulus, which is represented by E prime, is actually 3 times the shear modulus G prime. So this is a piece of information here. We're going to do check using different configurations and actually check theory with all the results we're going to be producing. And we will be producing a lot of results in this work. The tread compound formulation comes up. There it goes. So it's a silica carbon black filled styrene butadiene rubber passenger tread compound. And there are 4 variations that we have with this compound. So it's the type of SBR. So we have a solution polymerized SBR, medium styrene, which is about 23 to 24%, high vinyl content. And we also have a functionalized solution polymerized SBR, medium styrene, high vinyl content as well, but with functionality. What we're going to change also in this compound is the mixing time. As you know, we need to mix at high temperatures to get the silanization reaction happening between the silane at surface with the coupling agent and with the unsaturation, the backbone of the SBR. Standard mixing time will be used, and we also threw in an extended mixing time to try to see if we get more silanization and better mixing dispersion. The caveat with that is that if you mix too much and with this material, you will also break down the polymer change. So there is definitely a compromise. You got to be careful with respect to mixing if you extend the mixing time. We cured all of these, the samples afterwards, 160 degrees between 22 and 27 minutes. More information about the actual formulation is given in the paper here at the bottom, paper 71, presented in 2011. So we have within the D&D, National Defense, a Metravib 450 DMA system. Here's a picture of it. You can see for this picture, I had it all cleaned up around because we had samples all over the place and everything. So I wanted a really nice clean picture for this presentation. Of course, all computer operated. You could see in the middle here where the sample goes. We have a heater here, and we could use liquid nitrogen to cool down, to do temperature sweeps. As well, we do have a cooling system as well that we can go down to -70 without using liquid nitrogen, which is also makes things a lot easier when we're testing samples. Now let's go over the different deformation modes or the configurations that we set up with the DMA. So for the shear testing, And I think you saw it in that little video that they showed in the beginning. In this case here, we have brass slugs, and what we do is we cure them together with our rubber. So the dimensions are given here, diameter, length. The sample width, you can see that it's a dual lap, so there's two samples in here, and it's about 2 millimeters in thickness. And what you do here is you insert that into the shear testing configuration. And if you could see here, you can see where the rubber is, right here and here, the black in between, if you can see my arrow with the presentation. And we do the testing, frequency is at 1 hertz, and the amount of shear we apply is plus or minus 5%. So that's our dynamic displacement. Tension configuration. So here's the sample, just coming out of a tensile sheet, thickness 2 millimeters, width is 12.7 millimeters. Grip separation, that depends. If we're doing a temperature sweep, it's 10 millimeters. If we're doing a double strain sweep, it's 5 millimeters. And we do all these dimensions because we want to limit the shape factor correction when we get the final results. And the compression configuration. Here you have it. We make cylinders. In the cylinders, the height is 12.7 millimeters, diameter is 6.3 millimeters. Of course, when you're doing compression testing, you have to glue the samples to top and bottom. Don't forget to do that. Very important. Now let's go to temperature sweep. So for the tire testing and tire prediction, temperature sweep is very important. And I give you here the different experimental setups that we do use. So I talked about the shear, compression, also 1 hertz. So in compression, you have to take and you have to use a static strain of minus 2.5%. Dynamic strain afterwards is 1.25%, plus or minus 1.25%. Tension is just the opposite of compression. So we're going to have to stretch the sample 2.5%, and then we oscillate it at 1.25%. Heating rate is 2.5 degrees per minute. And what we do is we collect data at minus 20, minus 10, 0, 30, and 60 degrees Celsius. So when we set up the temperature sweep, we actually let plateau at each of those temperatures, and we collect at least 40 data points, and we take the average of those data points. So we collect a lot of data in the end. And I'm showing you here in the graph an example. So with the solution SBR standard mixing time in the shear mode, what sort of data do we get? So you can see with the temperature sweep starting at minus 20, winter traction characteristics are at minus 20, and looking at the storage modulus. Ice traction techniques at minus 10. Wet traction at 0 degrees Celsius is with 10 delta. Then the rolling resistance or fuel economy. With the temperature sweep, we looked at not only 60 degrees Celsius, which is normal, but we also looked at 30 degrees Celsius. So the two different temperatures. And of course, it's 10 delta that we want to look at. Double strain sweeps they're done at 1 hertz and 30 degrees Celsius. And again, I show the example with the solution SBR standard mixing time shear mode. And what I'm showing here is the storage modulus as a function of dynamic strain. What we do is we collect, we have 13 different strains that we apply to the sample, starting from a very low strain up to a strain of, this is 50%. And what happens? So we do 2 passes. So pass number 1 is the blue. We start out here, high storage modulus, and then the storage modulus goes down, 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 down. And then we bring it back and we start over again, pass 2. And you can see that all the values are lower on pass 2. And if you keep going, you do pass 2, you do pass 3, pass 4, you don't see that much of a difference between pass 2 and afterwards. But I've seen people go up to maybe past 10, even that. But anyways, what information do we get from this? Well, the first piece of information, we get the Payne effect. So the Payne effect here is the difference between the two numbers of storage modulus. You can see from the top here down to the bottom. So the Payne effect is really what we're doing is we're breaking down all those wonderful filler elastomer interactions. We put so much time into mixing the compound to get that carbon black or other fillers incorporated. With respect to doing dynamic strain, as we're doing here, high strains, we break down all those great interactions. But you can see what happens is that when we go back to this sample afterwards, let it relax, we do gain back a certain number of those interactions. And those interactions are given by the Mullin's effect. So you can see at that low strain, the Mullin's effect, it's a lower number than the Payne effect. So the Mullin's effect, yes, it has definitely has something to do with the interactions between the elastomer and the particles, but it also has to do with the elastomer chains as well. Are we breaking some of the crosslinks as well, some of the weak crosslinks in the material? Do we have slipping and sliding of chains taking place? It's a very complex phenomenon there as well. So these are the two different effects that we're going to be measuring as well in this study. And I got the arrow down here at the bottom that you can see. It's at about 5% strain. We're going to be collecting the data at 5% strain in order to use them for our tire predictor data. Here's our tire predictor data for DMA testing. So we can get information from different tire tread characteristics. You can see here on the left-hand side, rolling resistance, for example, we're measuring it with tan delta, with the temperature sweep at 30 degrees and 60 degrees, but we also get it from the double strain sweep at 30 degrees Celsius. And we can get also information about dry handling, dry traction, and you can see the DMA properties that we could see here, storage modulus, loss compliance. And what's important is the property improvement. So a lot of this is empirical. The people are doing work in this area and like that. But we know that if we can lower the tan delta, we lower hysteresis, lower the heat buildup, that this is good for rolling resistance and good for fuel economy. It's well known wet traction is done temperature sweep at 0 degrees Celsius. We look at tan delta, we want a higher value for the tan delta at 0 degrees. And the same thing for ice traction, but at -10. Winter traction, -20, we want a lower storage modulus. So this sort of makes sense because when you have by your winter tires, they are softer than your summer tires or all-season tires. Softer meaning that the storage modulus will be lower. So we want a lower storage modulus at -20 for better grip and better traction. Now what I'm going to do is I'm going to go through the results, and I like the way the results are presented on the spider graphs because it's very easy to see. And I'll present the results for the different deformations. So shear, tensile, and compression. We'll start with shear because shear is most commonly used for entire testing. And I've got the 4 different compounds given here. So the standard is black, it's solution SBR standard mix. The green is the SBR extended mix. The red is the functionalized solution SBR standard mix. And the blue is the functionalized standard SBR extended mix. So I'm not going to go through all the tire predictors because it's a lot of data, as I mentioned to you before. But I will make a few comparisons though. So the data we get from the double strain sweep is with the asterisks. So we have the fuel economy up here, we have dry handling over here, and we have dry traction down here. So what I'd like to compare is double strain sweep to temperature sweep, for example. So the fuel economy is showing good comparison between the two. So fuel economy here is this is the temperature sweep. And you can see, for example, for the functionalized SSBR, numbers are looking quite similar. So that's good to see. That's very good to see. All in all, we've collected 12 different predictors here. I will concentrate on the blue just because it's easy. And you can see that with the functionalized SBR, we're getting better rolling resistance, better fuel economy. We're also getting better winter traction. Why is that? I didn't tell you in the beginning, but the material does have a slightly lower glass transition temperature, so it is going to help, for example, the winter traction. However, there's always trade-offs. There's trade-offs. And when you look here, for example, at some of the dry handling here, dry traction with the blue, we do lose out versus the standard mix or the standard SBR. Now let's have a look at some of the other, the tensile data. Tensile data looks sort of similar to what we saw with the shear, what we expect, right, from theory. Again, the better rolling resistance of the SBR compound, the functionalized SBR compound, better winter traction. Again, it seems to be worse when it comes to the dry handling and dry traction. So again, trade-offs here are seen. And let's go next to compression mode. Compression seem to show most difference. Again, we do pick up the better rolling resistance with the functionalized SBR, which is nice to see, and the winter traction as well. Not as prominent as the other tests, but we do seem to lose out here on the dry traction. We see a lot compared to the standard mix and the standard SBR. So we do see deviations here. So in a nutshell, I'm going to try to afterwards explain why we're seeing those deviations, but just food for thought, something to think in mind if you are doing different deformation modes and doing testing with your DMA. I wanted to throw this in to show the Mullins and the Payne effects again, and just point out here, you can see the magnitude, depending on whether it's shear, tension, or compression. Obviously, when we're in shear, we're talking about much lower values. But when we go up to tension or compression, we see much bigger effects here on the moduli. The one thing you have to be careful about here is that if you are using cylinders or doing compression, is that we cannot get to the high strains as we can with tension or shear. Tension and shear, we get up to 50%. Compression, after a while, you keep pressing down on that cylinder, it's just going to buckle and you're not going to get down any further. And that's what we're seeing here at about 20% compression here, 20%. So it's something to keep in mind. The other thing, and that I wanted to show here with this slide, is just the fact that the Payne effect is a much bigger effect than the Mullins, just with respect to the magnitude. And I'm showing here for the shear, tension, and compression, but just the values here of the storage of moduli are less compared to the Payne effect. Remember, this is a log scale on the Y, so the effects here are actually much bigger than what they appear. Now let's get back to theory, compare with theory. And let's look at, I just picked out some of the graphs from the paper, fuel economy. That's 60 degrees in a temperature suite. So when we look at, for example, tension and compression, so we measure tan delta by tension or by compression, we got 4 data points. All right, so we're putting in the straight lines, 4 data points. I know there's going to be a little bit of error with this. But we don't find the slope here, we should be 1-to-1, right? Between tension and compression, 1-to-1. It's about 1.2, so there's some deviation there. But where we see the big deviation is when we compare tension shear, compression shear. So this is the pink and the blue ones over here. You could see here that look at the slopes are about 2. They should be 3 compared to theory. So we have an idea why that is so. I believe it come up in the next slide. Look at winter traction. Remember I talked about storage modulus. Here we look at the tension shear, compression shear. Numbers look a little bit better. We're closer to 3 here. We got a 3.3 and we got a 2. Again, we're off of the tension compression. It's 1.3. It should be 1, the slope. So definitely there are some deviations around the E prime equals 3 G prime and the tension compression, which should be 1 to 1, according to theory. So why is that so? First thing, chemical cross-link density. So as you know, the different samples that we made, so that the tensile sheet, the shear specimen, as well as the compression set button, were made cured at 160 for a certain amount of time. And you can see that when we look at their actually crossing densities, the shear in particular here, which is the purple, is a lower crossing density in all cases for the 4 mixes. The tension and the compression are much closer, but they still have some difference between them. So in particular here, we're just highlighting the fact that the shear specimens possess a 10 to 15% less crossing density. Crossing density, of course, is going to be proportional to modulus. So that's going to definitely affect the shear modulus that we're seeing. So we're going to get a smaller value for the shear modulus under shear. So that's one thing to consider, why we're seeing differences. The second thing is nonlinear low strain behavior. And when we use the DMA here, we just do regular stress strain under tension, shear, and compression. What we noticed was that with the tension compression, which was a bit strange, if you look at the let me see here, the dark blue and the red, those are the standard mix samples. There's lots of curvature in the low strain area, so it's non-linear. It's interesting when we go to an extended mix that it seems to straighten out much better, so it's more Hookean in that area. And we want the more Hookean behavior in order to have more agreement with theory. So this is another factor which is going to affect and give us nonlinearity in our results. Now I'd like to conclude. I think you'll agree with me that using the DMA, in our case, the Metravib DMA, is very useful for tire prediction data using tension, compression, or shear modes. Which mode you use, I mean, it's up to you. Shear is used most of the time, but tension is actually quite easy to do as well. Compression is probably maybe the more difficult one to use, but it can be used. What we saw in the results, the functionalized SBR is superior for improved fuel economy, dry handling, and winter traction. But we found that the regular SBR is superior for ice, wet, and dry traction. Increasing the mixing time is beneficial for fuel economy and winter traction. And so why is that? Increase the mixing time, more silanization, more bonding between the silica and the chains. That's going to reduce the hysteresis and give us a lower tan delta and better rolling resistance. Why better winter traction? Probably because the fact that we're mixing it longer, we're breaking down more of the SBR chains, so we have more chain-free ends, and we have a material which will have a lower storage modulus at -20 degrees Celsius. And finally, cross-link density differences of the test specimens, as well as nonlinear stress strain behavior, can explain deviation from theory. And before I go to questions and answers, I just wanted to bring up a couple Chemical Institute of Canada events coming up very soon. We have our Rubber Chemistry and Technology Division virtual seminar, December the 4th, with Professor Gilles Arsenault from the University of Western, talking about butyl rubber and tire treads. Probably the holy grail in tire treads. How can we get butyl into tire treads? That would be a mine. It's a mine worth mining. And finally, we have a big event next year, the Canadian Societies for Chemistry and Chemical Engineering 2026 is in Toronto, May 24th and May 28th. We're going to have 3 rubber technical sessions: general advances in rubber technology, TPEs and TPVs, and also resolving rubber processing issues. So we hope that you could be with us in Toronto as part of in supporting the CIC event in Canada. So I am done with my presentation area. Is it now the time for questions?
Thank you, Richard. Before we go to the Q&A, I'm just going to throw it over to Arya Shoro-Stembik to take us through a little bit about some of our DMA capabilities, and then we'll go into the outro and Q&A.
Okay.
All right. Hello, everyone. My name is Arya. I'm a lab scientist at C-Therm Technologies. I'm going to talk about Metravib DMA instruments. Thank you, Richard, for your informative presentation. And so I'm about to share some slides here. Alrighty. Okay. So C-Therm Technologies is partner with Metravib instrument material testing. We present dynamic mechanical analysis instruments. Metravib provides a variety of instruments from low force or desktop series DMA, DMA plus series, and high frequency DMA, which can go to very high frequency of 10,000 hertz experimentally. Today webinar, I'll be focusing more on plus series and the advantages of this series of instruments and how they can add value to your lab and your research for a variety of industries. So DMA plus series, we have 3 different DMAs for this series, and from plus 300, plus 1,000, and plus 2,000. So moving forward, so plus series stands for high performance DMAs. So these DMAs are high performance machines that can give you more accurate results with more capabilities. For example, they are capable of running fatigue testing. They're not limited only to dynamic mechanical analysis, providing hysteresis curve for nonlinear analysis of the materials. If you're having a simulation or any research that is related to nonlinear analysis, Metravib DMA is the only instrument that can provide you with hysteresis curves. Crack growth testing that follows standard ISO 27727, which is another unique capability that Metravib instrument provides. Heat build-up, which is also type of fatigue testing, very important for tire industries, and automation of the dynamic mechanical analysis using robotic arm called Expander. I'll be sharing more information for each title, but just want to mention quickly some capabilities. And of course, Plus Series instrument, they're not only a DMA, but also they have static capabilities, for example, testing like stretch relaxation and prediction of long-term creep behavior. And they are suitable for testing materials from a range of very soft materials to very stiff materials, and in variety of frequency starting from 10 microhertz, so very low frequency, to higher frequencies as 1,000 hertz experimentally without any correction. And everything is measured during the experiment. The temperature range for this series starts from minus 150 with liquid nitrogen to 500 degrees C. And as Richard mentioned, you can have access to minus 70 using a chiller without having liquid nitrogen. Yeah, so let's take a look at the DMA Plus series and why we can obtain significantly improved results with higher accuracy using this instrument, and how this instrument is capable of providing some unique features like high frequency all the way up to 1,000 hertz. So this is thanks to rigid frame of the instrument design. And as you can see, this rigid frame provides a very stable instrument structure for high frequencies test. A very common challenge for high frequency testing is that usually the instrument starts moving itself. So in a more technical term, we call it compliance. So when you're running a test, you see also effective, not only the sample is deforming at higher frequency, but also the instrument is also being deformed, and like it's moving and sort of resonates with the sample, which can introduce a significant error to your measurement. Some ways of addressing this issue might be applying correction. However, it's definitely more reliable to have a solution without having to apply any correction to that, just to limit different sorts of errors. For this purpose, this design helps a lot. So you limit any compliance factor to contribute to your testing. And also it helps to provide high accuracy measurement for high strain and for softer material, low strain. So moving forward, talking a little bit more about capability of Metravib DMA. So as you can see in the chart here, classical DMA, they cover a limited range of stiffness, something around 100 to 10 to the power 6 Newton per meter stiffness. Plus series DMA, plus 1,000 and plus 2,000 goes and beyond that range to 10 to the power of 10 to the power of 7 for stiffness. However, the DMA plus series even takes one step further, and it goes to very low range for stiffness. So it's very suitable for low stiffness material. I know that many folks in medical devices and biomaterials, they're interested in capability of testing materials with a very fragile material with low stiffness. So this instrument can help you a lot with your testing for those materials that are low in stiffness. However, with having this instrument, you also open the window for your capability to test very stiff sample. So it's not limited, but it has added values to itself, which is quite impressive for a DMA. And as Richard mentioned, having a DMA in Tire Labs for different and the information obtained from this test method is very important. Already, so going through some other capability, for example, fatigue crack growth module. As I mentioned before, it's ISO 27727 for rubber and polymers. It basically has a unique test setup. There is a camera with the resolution of micrometer, and it can track the crack propagation into the sample. Moving forward, I talked about automation of the Plus series. This is very important these days for different industries, folks that they want to dedicate their people on their technical side and to more interpretate the data and use that time to analysis the data instead of just running and operating the instrument. That can be very useful for those folks. And it's a very helpful setup for automation. You can see on the left-hand side the robotic arm, which is expander. You can run the tests for DMA testing for deformations, including shear deformation, tension, and compression. This test can be run 24/7 without any limitation. All you need to do is to put the samples in the sample rack on the left-hand side, and everything else will be done by your robotic arm. And also you can see the situation with your testing on your cell phone, and it can be monitored using your smartphone, and it lets you know by text messages or emails that what is the condition with testing and how your testing is going on. There's a closer look to expander. This is a shear deformation, and Richard also mentioned this deformation during his. And as you can see, this is a dual shear gap, two rubber samples in between. And the robotic arm is basically setting up the test. So definitely having robotic arm can improve capability of the testing, for example, quality of the testing, for example. It reduces and it removes a human error for tests. It increases the reproducibility. And it improves the standard deviation of the testing. For example, this is one example of running of the tests, same test with an operator and for one series of testing, and you see the standard deviation, and on the right-hand side, you see how expander can improve those numbers. Yeah, here I'm going to talk a little bit about Dynaplus software, which is the software we had Metravib DMA uses to evaluate and analyze the material. On the right-hand side, you see the crack growth module. As you can see, a high-resolution camera tracks the crack propagation in the sample. On the left-hand side, you see the hysteresis loop, which is, again, the nonlinear analysis of the material. This is very unique to Metravib instrument. And Metravib DMA is capable of providing hysteresis curves for those folks who are modeling and need the data for simulation or error calculation. And Dynaplus software is one software, and everything is provided within one software. It can control everything. As you can see, for example, here, controlling the setting up the test for the deformation mode. All those nonlinear deformation, all the test parameters, everything is controlled within one software. And also, you can have fully have access to the raw data using exactly, again, same software. Other capabilities of instrument is having this capability to make time temperature superposition curves for evaluating materials at frequencies higher than 1,000 hertz. That DMA Plus series is capable of doing that, creep relaxation, and long-term creep behavior up to years within one software. And on the right-hand side, you see some screenshots of the test results of the DMA test. And this is fatigue testing. For the last slide, you can see the different fatigue testing mode for crack growth module. And heat buildup. We can also have that the waveform you're applying for fatigue testing. You can customize it. There are some predefined waves, for example, a sinusoidal or Harvard sine or pulse or triangle, square, and you can build your own wave to be applied for different application on the sample for fatigue testing, which is, again, very useful for some unique applications. And last but not least, here is my slide to wrap up this presentation here. Here at C-Therm Technologies, we have a DMA Plus 300 instrument that we provide different kinds of testing. If you're interested in DMA testing for your material, for glass temperature, and master curves, creep behavior, curing process, Payne effect, or Mullin's effect, and all those important information that you might need for your research, please feel free to shoot us a message, and we'll be more than happy to do. Thank you so much, everyone, for attending this webinar.
All righty. So yes, folks, wrapping things up here today. I'm just going to close out our session here very quickly. If this content was interesting and you wanted to maybe see some similar discussions on whether it's thermal conductivity testing, DMA, or thermal analysis, we do have past webinars and a tech library available on our website. Looking through upcoming webinars. We are looking at the next one, November 11th at 1 p.m. on a guide to method selection for thermal conductivity testing. And then the next one following this will be December 2nd, taking a look at an application of fumed alumina. Upcoming events, so Richard had a few posted from his side and from C-Therm's side. We will be at the Thermal Management Expo in Europe, November 11th. We will have a booth and be presenting there. Also in a live event coming up in Poland on November 20th, just the week right after that. So as Ari had mentioned, for the DMA side, we offer these testing services, Rigaku, Metravib options through our thermal analysis labs group. These are certainly testing capabilities that we are happy to support groups with their research. If you did have any need for any of these tests, please feel free to reach out. We can certainly also schedule more of a in-depth technical consultation where we go into some of these methods in further detail, provide you with some information on how this type of testing would work for your samples, potentially even if you wanted to bring some of these capabilities in-house. That being said, if you did want some budgetary information for any of our core equipment or any of the groups that we represent, please feel free to reach out about that. We're certainly happy to provide a quotation. For the folks on the line that are from the academic sector, I will make note of C-Therm's academic support program for our Trident platform. If you are interested in thermal conductivity testing and you are coming from a university or a academic group, please feel free to reference this, and we'd be certainly happy to keep you updated on what that would look like in terms of cost and budget. My last little request here is to give us a follow on LinkedIn. This is where we do post all of our latest and greatest content, upcoming content pieces, webinars, etc. So if you are looking to keep up to date on what is being presented and what we're talking about, this is going to be the best place to do so.